section 8. So in this section, we're going to talk about static aeroelastic and trim analysis using the trim module of ZAERO. The trim analysis solves a set of unknown trim variables and or trim degrees of freedom for the balance of the 6 degrees of freedom forces and moments of our CG between the aerodynamic and inertial forces. So the trim module treat the aircraft as a point mass. So this point mass has 6 degrees of freedom, and then we define the trim variable vector A. So any parameters that can change the aerodynamic forces can be defined as a trim variable. So alpha is the angle of attack, beta is the side slip angle, P is the non-dimensional roll rate, Q is the non-dimensional pitch rate, R is the non-dimensional yaw rate, and delta is the control surface deflection angle. And so we may have a C set of a number of control surfaces. The trim degree of freedom vector contains the acceleration at CG. So nx, ny, nz are the accelerations along xyz axis. P dot, Q dot, R dot are the angular accelerations about xyz axis. So the net distributed forces on the structure is the difference between the distributed aerodynamic forces and the inertial forces. So this net force applied to the structure. So the KGG is a G-set stiffness matrix. X is a G-set structure deformation. Now, if you integrate this net force about the CG, and so the net force at CG and the moments are all 0. That's guaranteed. And how do we calculate the distributed aerodynamic force vector? So the total distributed aerodynamic forces consists of the incremental aerodynamic feedback force due to structural deformation and the aerodynamic forces on the rigid aircraft. So this is incremental aerodynamic feedback force due to structural deformation. This is the forces on the rigid aircraft. The incremental aerodynamic feedback forces can be related to the structural deformation by the AIC matrix. So if we have the G-set structural deformation multiplied by the spline matrix, and then we will transfer the deformation to the K-set. And AIC times K-set give us the aerodynamic forces at the K-set. Then we use the transpose of the spline matrix times the dynamic pressure. That will give us the aerodynamic feedback force due to structural deformation. And for the forces on the rigid aircraft, we can do a Taylor's expansion, expand about this mean flow condition, and then times the alpha partial F partial A times A, and partial F partial A contains the distributed aerodynamic force derivatives with respect to the trim variable. Okay, so partial F partial A also can be computed from the AIC matrix. So the phi R is the rigid body modes, and phi C is the control surface kinematic modes. So this multiplied to that will give the partial F partial A in K-set. Then we use the transpose of the spline matrix, transfer those forces to the G-set. And F naught K is the K-set aerodynamic forces at the mean flow condition. It's called thicken due to thickness and camber of the configuration, and the mean angle attack alpha naught, mean side slip angle beta naught, mean control surface deflection delta naught. So those alpha naught, beta naught, and delta naught are specified in the trim flat car. Trim flat car is referred to by the MK LZ car. The thickness and camber is defined in the PA47 car, So all the aerodynamic forces are computed at k set, and it can be mapped back to the g set using the spline, the transpose of the spline matrix. The total distributed inertial force Fi is due to the acceleration of the rigid aircraft u double dot and the acceleration of the structure. So if we have mgg matrix, multiply x to the x double dot and u double dot, and that will give us a distributed inertial forces. But however, in the trim module, we assume the x double dot to be 0 because the trim analysis is a static aeroelastic problem that does not involve the structure oscillation. So if x double dot is not 0, the response of the aircraft becomes a dynamic loads problem. So in ZAERO, the maneuver loads module, the gas loads module, the store ejection module, they all belong to the dynamic loads module. The U double dot can be U double dot in GSAT can be related to the trim degrees of freedom by the rigid body mode. So this is the rigid body mode times the acceleration at CG will give us the distributed acceleration in GSAT. So the distributed inertial force is mgg times the rigid body modes and times the accelerations at CG. And then if we plug back this equation and those equations back to this equation, then we can obtain this equation. So then we further assume the GSAT structure deformation can be superimposed by the elastic modes times the generalized coordinates of the elastic modes. So phi E is the elastic modal matrix, excluding rigid body modes, because the rigid body modes cannot produce internal loads in the structure. And so for a whole aircraft structure, normally the lowest 50 to 100 elastic modes are sufficient to achieve a convergent solution. Okay, then so we substitute this equation into in here and in here. Then we pre-multiply this equation by the transpose of the rigid body mode. Then we will find out we can get rid of the KGG, because KGG here and this is the elastic mode, this is the rigid body mode. So this one is 0 because because the elastic mode and the rigid body mode, they are orthogonal to the KGG. So we have the remaining terms. MRR is the MGG pre and post multiplied by the rigid body modal matrix. So it's a 6x6 rigid body mass matrix. And in fact, this is 6x6 rigid body mass matrix is identical to that used by the flight dynamic people. And then next we pre-multiply this equation by the transpose of the elastic mode. We can get rid of the MGG because the MGG because phi E and phi R, they are orthogonal to the MGG matrix. So we have this equation. Then we can invert this matrix, and so we can then we substitute the QE into here, okay, and where the KEE is the generalized stiffness matrix of the elastic mode. QEE is the generalized area forces of the elastic mode at the K equals 0. Because this is a static area elastic problem, we only need ASC at K equals 0. And therefore its imaginary part is 0, so it's a real matrix. And then after we substitute QE into this equation, we can write this equation in a general form. We call MRR times the acceleration at CG equal to FR bar times the trim variables plus the mean flow forces, where FR bar is expressed here, and where A bar is this equation can be calculated from AIC and also from the inverse of this matrix. This is so-called the aeroelastic amplification matrix. So if you don't have A bar, this become a trim equation for the rigid body aircraft. Now let's look at what this matrix means. So if we don't have A bar, and in fact, all the coefficients in this matrix is the aerodynamic stability derivatives of each trim variable. For example, this is CD naught, CD alpha, CY alpha, CL alpha, and so on. If the second trim variable is beta, this is CD beta, CY beta, CL beta, CL beta, and so on. Now, if we look at this equation, that contains, if we assume A bar to be 0, is the mean flow, the aerodynamic force and moment coefficients at the mean flow condition. Therefore, those coefficients can be replaced by the user supplied value obtained by the wind tunnel test or CFD. So once you import the rigid stability derivatives, all the aerodynamic forces and moments, and the trim module will flexibilize those rigid value using the A bar matrix. So give you the simplest trim problem, which is a 1G trim equation. So NZ equals 1. That requires the weight of the aircraft equals the lift. So W is the weight, NZ equals 1. So this the 1G condition, and will be equal to the total lift. The total lift is CL alpha times alpha plus CL naught. So if this is CL with alpha diagram, this guy, this point here is called CL naught, and the slope of this CL with alpha line is the CL alpha. So we can solve the alpha. Then we can solve, say, if we want to achieve 1G cruise and of the aircraft, then we can solve the angle attack. In this under this angle attack, the aircraft can create lift, which is equals to the weight of the aircraft. Okay, then this trim equation can be split into the UR double dot and A into a given set and unknown set. So UR double dot can be split into UG double dot and UU double dot. G is given, U is unknown, A is AG and AU. Then we split this into two parts, then we rearrange this matrix. So all the unknown on the left hand side, all the given on the right hand side. So we have this matrix, and then if this matrix is a square matrix, we can invert this matrix and get solve the unknown trim degrees of freedom and trim variable. Okay, to calculate the aeroelastic amplification matrix, we need to invert this matrix. So in what kind of condition this matrix becomes singular? And so we treat the dynamic pressure as an eigenvalue problem. So we found that the lowest real eigenvalue of this matrix. So the lambda lowest is so-called divergence dynamic pressure, at which the structure encounters the so-called divergence problem. So prior to the trim analysis, lambda loss is always calculated first to ensure that the input aerodynamic pressure for the trim analysis is below lambda lowest. If it's higher than that, that will lead to fatal error. So lambda lowest is the divergence dynamic pressure of the restrained structure, no rigid body mode. For the supported structure, lambda agrees with the divergence dynamic pressure with a zero frequency calculated by the G method factor analysis. For the free structure, meaning you have a rigid body modes, the divergence dynamic pressure calculated by the G method is usually slightly higher than the lambda lowest and associated with the small non-zero frequency. The divergence of free structure is called dynamic divergence. This because for a free structure, when the structure encounter divergence, and for example, the wing has a large torsion deformation that will create lift. This lift can lift up the whole aircraft weight and become a solitary type of a response. And because it involves the total weight of the aircraft, the frequency is small, but it's not exactly zero. And also, in what kind of condition this matrix become a square matrix, so we can invert that. If the total number of unknown degrees of freedom and unknown trim variables equals the number of trim equations, then this matrix become a square matrix, and we can directly invert this matrix, and this equation is called determined trim system. So to give you one example, if I want to achieve 1G cruise condition, and so the equation is the lift equal to weight, and the total pitch moment, the Cm equals 0. Then I have two trim variables, and the angle tack and the horizontal tail deflection angle. So I have two unknowns and two equations. I can solve the angle tack and the control surface deflection angles to achieve this 1G cruise condition. And this is called determined trim system. If the total number is less than the number of trim equation, this is called underdetermined trim problem, and it's unsolvable. For example, for the 1G cruise condition, if I lost my horizontal tail, I only have one trim variable, which is angle tack, then I cannot solve this trim problem, and meaning the aircraft going to crash. If the total number of the unknowns is greater than the number of trim equations, this is called overdetermined trim system. To solve the overdetermined trim system requires the minimization of objective function and while satisfying a set of constraint functions. So, for example, the active aeroelastic wing has 4 control surfaces, 2 at the leading edge, 2 at the trailing edge of each wing. So we want to maximize the roll rate, and by finding the optimal control surface deflections, but each control surface the hinge moment cannot exceed a design value. So this become a constraint function, and this become the roll rate become an objective function. And another example is minimizing the wing loop bending moment of a joint wing that has 3 control surfaces on each wing, while the control surface deflection angle must be within an upper and lower bound. So if the joint wing is going under a 2.5 G pull up, we want to find out what's the best control surface deflections, which can minimize the wing loop bending, while the control surface deflection must be within upper and lower bounds. So this is a typical optimization problem. So uh, so the ZAERO trim module employs the modal approach, whereas the natural trim module uses the direct method. And what is the direct method in natural? In natural, they use the ASAT stiffness matrix, then they spline the AIC into ASAT. Then they combine those two matrices, and they need to invert that or decompose that matrix to solve the unknown trim variable and the structural deformation. This matrix is fully populated and asymmetric. So if you have a large structural model and you have large ASAT degrees of freedom, this becomes very expensive. And so, however, if we use the modal approach, no more than 100 mole are sufficient for a modal approach to converge. So on the other hand, if you use the direct method, it may require a large computational time. And also the ZAERO trim module is capable of dealing with both determined and overdetermined trim system, whereas the natural trim module can only handle the determined trim system. And for the symmetric configuration, okay, so symmetric about the XZ plane, ZAERO trim module only requires a half-span structure and aerodynamic models, even for asymmetric trim condition. For example, if the aircraft want to achieve a 4G rolling pull out, so this is an asymmetric condition, and the ZAERO still can use a half-span model to solve this asymmetric trim condition. However, the natural trim module always requires a full span model for asymmetric trim condition. So internally, ZAERO will decompose asymmetric trim condition into a symmetric condition and anti-symmetric condition. Then you solve the symmetric trim variable and the anti-symmetric trim variable. At the end, you will superimpose them together to give you an asymmetric trim solution. And then you may ask, the static aeroelastic problem is a static problem. Why the mode shape is involved? Because mode shape is calculated because mode shapes depends on the stiffness and the mass of the structure. The mode shapes are treated as a set of shape functions. The deformation of the structure is assumed to be superposition of a set of shape functions. Because the mode shapes satisfy the boundary conditions of the structure, they are the best shape functions. The common misconception of the modal approach versus the natural direct method for static aeroelastic analysis is that the modal approach depends on the mass distribution of the structure, whereas the natural direct method does not. So this is a misconception because for a free structure, the flexible aerodynamic stability derivatives computed by the modal approach is nearly independent of the modes as long as the center of gravity is invariant. And because even you want to use the direct approach of natural, and then natural use the inertial relief for the free static aeroelastic analysis. And therefore, even the direct approach involves the mass matrix. So the mass matrix is involved in both the modal approach and the natural direct method. Thus, if the CG is changed, the solution of both the modal approach and the natural direct method change. If all masses in the structural model are scaled by a factor, so therefore the CG is unchanged, the flexible aerodynamic stability derivatives of both modal approach and the natural direct approach are unchanged. If for the supported structure, so you have no rigid body mode, the solution of the modal approach is independent of the mass matrix. Any mass matrix gives the same flexible aerodynamic stability derivatives. So this this example is for a swept wing, and and uh, and here is a CG, and we have a 3 rigid body modes, and so it's a free structure. Now, if we use the nominal mass, this is the natural frequencies, and this is a flexible stability derivatives. If we multiply all mass in the structure by a factor of 0.1, and the structure become lighter, so the natural frequencies increase. But you calculate the flexible derivatives, they are unchanged. If you multiply all masses by a factor 2, the natural frequency decrease, and the flexible stability derivative still unchanged, because if you scale all masses down or up, the CG is unchanged. Therefore, the flexible stability derivatives computed by the modal approach are unchanged. And if we claim this point, so we don't have a rigid body mode. And so this is the natural frequencies, this is the flexible stability derivatives. Okay, then if we only perturb the mass at 100 and 112, if we only perturb the mass here, therefore the CG change. However, because it's a clamped structure, the flexible stability derivatives also are unchanged. So if you don't have a rigid body mode, it's independent of the mass distribution. And for the over-determined trim system, we use the optimization strategy to solve this over-determined trim problem. In general, the optimization problem can be formulated as minimizing the objective function, which is function of x. X is the design variable, meaning the unknown trim degrees of freedom and trim variables. And also we have a constraint functions, the g of x less than and 0. So we can impose many constraint functions. And the ZAERO requires the user to define a set of a trim function. The trim function is a function of the unknown trim degrees of freedom and trim variables. So this trim function can be a section load, like a wind loop bending, wind loop shear, and grip point displacement force, element stress and strain, aerodynamic forces, and moment, and so on. The trim function can be selected as the objective function or constraint function. So you can define a trim function, then you can use the trim function to construct optimization objective function, where C sub I is a weighting factor. And also you can impose the lower bound and upper bound on all the unknown trim degrees of freedom and the trim variables. And some trim functions require additional input via a sign matrix equals or DMI Boxer-Car. For example, if you want to compute grip point inertial force, you need to import MGG matrix. Once you have MGG matrix times the rigid body mode times the acceleration at the CG will give you the inertial load. And also, if you want to calculate the element stress, and you need to import the modal stresses. What is modal stresses? In that strength, if you use solution 103, which is solve the eigenvalue and eigenvector of the structure and give you the mode shapes, then you can ask net strength to treat each mode shape as a deflection. Then under this deflection, you can ask I want the stress in a given element. So, for example, if you have 10 modes, and naturally will give you 10 modal stresses in this element, and you can import those modal stresses into trim module, and after trim module solve the generalized coordinate of the elastic mode, and you can use this equation to calculate the stress in this element. Okay. Now, the Bokita cars for trim analysis, the top level car is trim. Okay, so this trim cars is referred to by the trim case control command. The next important car is called trim var car. The trim var car, you define a trim variable, and this trim var car is referred to by the trim car, and also you can link you can link one trim variable with many other trim variables. And give you one example. For fighters, if you have a so-called flap scheduling, the leading edge flap deflection and trailing edge flap deflection angles is a function of angle tag. So you can link the angle tag trim variable with those control surfaces. And then you have trim function car. This trim function car, you define a trim functions. Okay. Then if you have an overdetermined trim problem, you have to define the trim obj to define a objective function, and the trim count to define a set of constraint functions. Then those two cars refer to the trim function car to construct the objective function and the constraint functions. Finally, you have a plot trim car, and the plot trim car, you can use the plot trim car to generate a graphic file for displaying the deformed aerodynamic model under the trim loads. Or you can ask the plot trim car to generate a file that contains the fly loads in terms of natural force and moment Bogota cars at the structural finite grid point, the GSAT. So the user can insert this file back to the finite element model to perform a static aeroelastic analysis. And so you have a trim car here, and this car is activated by a trim case control command, and then you can use the plot trim car to output the graphic file or the force and moment cars. And then if you want calculate the inertial loads, you need to import the SMG and AMG matrix. This is for symmetric, this is for anti-symmetric. But you don't need to import this. All you have to do is to import the MGG matrix. The trim car refers to MK LZ car. You will grab the AIC at k equals 0, and also grab the Mach number and the mean flow condition. Then you need to define the trim variable by referring to the trim var car. And then you in the trim var car, you can refer to a trim link car. You can link trim variables. And if you have an overdetermined trim system, you need to define the trim obj and trim count car. Okay, and those cars refer to a trim function car, and the trim function uses the trim function car to construct the objective function and the constraint function. And in the trim count car, you can refer to the load mark car. The load mark car, you can define a component loads. Also, you can refer to a DMI car to calculate the list of the modal values, like modal stresses. And also, the trim car refers to a set one car. In the set one car, you can list out the ID of the trim functions. And so when after trim module solve the trim solution, and it will further calculate the values of those trim functions, like a wing loop bending moment and so on. So this is the car. This is a trim car, and it has ID. This ID is referred to by the trim case control command, and ID MK refers to the MK LZ car, and the QINF you specify the dynamic pressure. If this is overdetermined trim problem, you have to refer to a trim obj and trim count car. and rho x, rho y, rho z is the CG locations relative to the REFX, REFY, REFZ, and those values are specified in the arrow z count. Okay, and the next you need to define the 6x6 rigid body mass matrix. So this is the weight. This is those are the moment of inertia. But however, if this is specified in terms of weight, you need to define the weight to mass conversion factor. For example, if this one is in pounds, and all but your aerodynamic model is the length unit is in inch, so this value should be 1/386. Okay, so the point one knows the g, the gravity is 386 inch per second squared. And the next one you specify the trim degrees of freedom, and which is UR double dot. you have three choices. It can be none, can be free, or a real value. If you say none here, and then this trim degree of freedom will be excluded from the trim problem. Okay, and if you specify a free, that means this is the unknown trim degree of freedom. If you specify value, then this is the given trim degree of freedom. And then those value can be either this one you specify true or G. If you say G, for example, if I want to do a 4G trim, and NZ you can say 4.0. So meaning is a 4G because the program knows the gravity is 386 inch per second square. Then the 4G will be 4 times 386. So you internally can convert the G into the true unit. If it's true, then you put a true unit here. And this is open-ended car. So after that, you can list the ID var and value pairs. Okay, and the ID var refers to a trim var count, and the value you have two choices. It can be free or real value. If it's a real value, this is a given trim variable. If it's free, it's unknown trim variable. So how do you determine this is a determined or overdetermined trim problem? You just count all the trim degrees of freedom which exclude none. So for example, I put none here, then I put either free or value in those 5 trim degrees of freedom. So I have 5 trim equations. Then you count all the free including the trim degrees of freedom and the trim variable, and you found that the free is also 5. Then this is a determined trim. If the free is over 5, then this is an overdetermined trim. And for overdetermined trim, you need to specify the trim OBJ and trim concat. And the trim var you give ID, you give a label. This label has 3 types of a trim variable. The first one is a program assigned trim variable, and it's hardwired label. So there's alpha meaning angle tag in degree. If it's beta, there is a side slip angle in degrees. If the P ray is row ray, the unit is PB over 2V. And Q ray is pitch ray is QC over 2V. R ray is yaw ray is RB over 2V. A thick cap is the mean flow condition defined by the trim flat cut, and also the PA 407 for thickness. And then you put the lower and upper bound of the trim variable. This one is activated only for needed only for overdetermined trim problem. And trim link refer to a trim link car. You can link this trim variable to other trim variables. And DMI, you can import the distributed aerodynamic pressure derivatives to replace the ZAERO compute value. So if you have some CFD compute pressure, and then at two different angle tag, then you can use finite difference to calculate the dCP by d alpha. If this label is alpha, then somehow you map this CFD compute pressure derivative to the ZAERO panels. Then you can import that into the DMI, and this for rigid pressure derivative. And then ZAERO internally will flexibilize those pressure derivatives. And the initial is the initial value of the trim variable, only used for the overdetermined trim system. So because it's an optimization problem, so the initial value may have impact on the final solution. And after that, this the aerodynamic force and moment derivatives with respect to this trim variable, and the default is none, and if it's none, and then it is then you use ZAERO internally compute derivatives, force and moment derivatives with respect to the trim variable. Okay, let's go back to the trim variable. This program assign trim variable. If the label you type here does not match the program assigned trim variables, but it match the label of the control surface, and this is a control surface type of trim variable, because it matched the label entry in the A sub Z car, AES link car, and the PCT mode, and the jet force and grid force car. So once you match that, and this is a control surface type of trim variable. Okay, if it does not match this and this, and then this is we call it user defined trim variable. So in this case, you have to input those force and moment derivatives with respect to this trim variable. For example, if I say label is thrust, then thrust it become a user defined trim variable. So you have to calculate the aerodynamic force and moments about the aerodynamic center with respect to this trim variable. So we have three types of trim variables, and ZAERO can solve the trim solution of an asymmetric trim condition, even if a half-span model is used. The asymmetric trim condition involves both longitudinal and lateral degrees of freedom, and both symmetric and anti-symmetric modes are required for the half-span model for solving the asymmetric trim condition. So you have to import the symmetric and anti-symmetric modes, and by two assigned FEM executive control command. And at the end, the trim module superimposes the symmetric and anti-symmetric trim solution to obtain the asymmetric trim solution. So the symmetric trim condition involves only NX, NZ, and Q dot. This is a pitch acceleration. So only those trim car for the longitudinal aerodynamic stability derivatives can be selected, such as alpha, Q, and the symmetric control surfaces. And then you need a symmetric mode. For the anti-symmetric trim condition involves only NY and P dot and R dot. And only those trim variable for the lateral aerodynamic stability derivatives can be selected, such as beta, P and R, and anti-symmetric control surfaces. Also, you need to import the anti-symmetric modes. The plot trim card can generate a graphic file, so you can display the deformed aerodynamic model under the trim load. Also, you can ask the plot trim card to output the natural force and moment cards in the GZ degrees of freedom, and then the user can insert this file into the natural input deck for a stress analysis. So this is the force and moment cards output by the plot trim card. And so the sample case is a forward swept wing with a canal and a vertical tail. So first, we want to define the control surfaces. The first control surface defined by the A sub Z car, we call it give a name called canal, and we say this is a symmetric control surface, and the CID refers to a contour car. This contour car to define the hinge line location, and because this is a positive integer, so the y-axis of this contour car is the hinge line location of the canal, and if this is negative one, then the z-axis of this contour car would be the hinge line locations, and it also refers to a panelist 3 car called canal. If this canal is defined by the CL7 car, and in the label entry in the CL7 is called canal, then panelist 3 will grab all the panels here and define as those panels for this control surface. So because it is a symmetric control surface, if the right hand side canal pitch up, its mirror image left hand side canal will deflect. We have a pitch up deflection also. The next one is called aileron, and we define as an anti-symmetric control surface, and 110 refer to this contour car, and whose y-axis is the hinge line location, and it refers to a panelist 2 car. Would define those list out the panel ID of those four panels to be the aileron. And the next one is we call trilogy flap, and this is a symmetric control surface, and also refers to the same contour car and the same panelist 2 car. So the same aerodynamic panel can be selected as an anti-symmetric control surface and a symmetric control surface. So at the end, the trim module will superimpose the anti-symmetric deflection and symmetric deflection to give you the net deflection of those panels. The last one we call rudder is anti-symmetric control surface, and this is the contour car. To the y-axis defines the hinge line, and it again refers to the panelist 2 car to list out the panel ID of those 4 panels for rudder. And because we are going to do an asymmetric trim, and only we have a half span model, so we need to import the symmetric modes and the anti-symmetric modes. And this symmetric mode has a 3 rigid body mode, which is 135. Anti-symmetric mode also has a 3 rigid body modes. Then we import the so-called SMGH and AMGH matrix. The SMGH matrix is calculated by MGG times the symmetric mode, and AMGH is calculated by MGG times the anti-symmetric mode. Therefore, you don't need to import 2 matrices. All you need to import is the MGG. Once you import MGG, the trim module internally will use those equations to compute SMGH and AMGH matrix for you. So the first case is asymmetric rolling pull out of the force by wind at the Mach 0.9 and the dynamic pressure equal to 1200 psf. And we only have a 5 trim degrees of freedom, which Ny equals 0, Nz equals 4.8 G, P dot, Q dot, R dot are zeros. And we define 10 trim variables. First is aileron equals 25 degrees, because aileron is defined as an anti-symmetric control surface. So the right hand side aileron is 25 degrees. The left hand side, the mirror image left hand side will be negative 25 degrees. Then this control surface can create a rolling moment. And we specify Q ray equal to this, rudder equal to 3, beta equal to 3, canard equal to 3, P rate, the roll rate equal to 3, and alpha equals 3, and the yaw rate equals 0, thick cam equals 1, and Trinity flap equals 0. So in this trim problem, we want to find out what's the angle of attack to give us a 4.8 G. And under this anti-symmetric aileron deflection, what kind of roll rate we can achieve? Okay. Meanwhile, we want to keep the P dot, Q dot, R dot to be 0. So we have to use rudder, beta, and canard to achieve this P dot, Q dot, R dot to be 0. And also the MK Aeroelastic car with ID 90 to generate AIC matrix at the Mach 0.9 and mean flow condition alpha equals 0 and canard equals -1. So this is the MK Aeroelastic car, and this is ID of a trim flat car. In this trim flat car, we see angle attack equals 1 degree, canard equals -1 degree, and we only need put one reduced frequency 0.01 here, and 0 we internally generate AIC for the 0 frequency, and we define 10 trim variable by 10 trim flat cars, and those 4 are the control surface trim variables: aileron, rudder, canard, and the Trinity flap, and we have upper bound and lower bound. And this trim variable defines the thick cam, and this aerodynamic loss due to the mean flow condition defined by the trim flat car. Then we have another 5 trim variables: alpha, beta, P ray, Q ray, R ray. So this is the trim cars, and with ID 100, and this 100 will be referred to by the trim case control command and equals 100, and this refers to MK Aeroelastic car, and from the MK Aeroelastic car we can grab the AIC at the K equals 0, and also the mean flow condition. This is the dynamic pressure, and then the rho x, rho y, rho z is the relative distance from the aerodynamic to define the CG from the aerodynamic moment center. The aerodynamic moment center is defined in the Aeroelastic car, so the REFX equals 15. So the CG location is 2.227 plus 15, and YCG equals 0, and ZCG equal to 0.0331. And then we put the aircraft weight equal to 16,000 pounds, and this moment of inertia. And because we need to convert the weight to mass unit, and the length unit of this aerodynamic model is in foot. So the gravity is 1/32.2. So this the WT mass factor to convert the weight to mass. And after that, we put nx equal to none, then ny equals 0, and nz 4.8, p dot, q dot, r dot are zeros. And so we have 5 trim equations. Then then we have a 100 which is canard 25 degrees, 700 which is Q rate, and the 300, 400, 200, and the 600 and 800 are all free. So they are the rather canard and alpha and the beta. So we have 1, 2, 3, 4, 5. We have 5 free unknowns, and we have 5 equations. So this is a determined train problem. Therefore, we don't need to specify train obj and train concat. We don't need to define the constraint function. And also in right here, if we say that this is G, then all we need to do for the NZ is put 4.8 G. Then because the program knows the gravity is 32.2, then 4.8 times 32.2 will become the true unit of the acceleration is in feet per second squares. And this 100 refers to 4 train function count. Okay, so when the train module solve for this train problem, it will calculate the value of the train function and print out in the standard output file. So those are train function. The first one we want to define the hinge moment of the right hand side aileron. So train function ID10, and it belongs to the aerodynamic quantity. It refers to the low Markov. In the low Markov, it defines refers to the contour car, and we want the moment about the y-axis to be the hinge moment. And this one is 2000. It refers to the panelist car, and in the panelist car, you list out the panel's ID of the aileron. Okay, and then we say this is because this is a half span model, and so the right hand side hinge moment and left hand side hinge moment under this asymmetric flight condition and should be different. So we want to say aileron right hand side aileron hinge moment. And 105 refers to a set 1 car. In set 1 car, we list out the grid point. This grid point is located within this right hand side aileron. And so this will give us aerodynamic force. This will give us inertial force. So the net load is the aerodynamic forces, the aerodynamic hinge moment, and minus the hinge moment due to the inertial load of the aileron. The next one is the bending moment of the right hand side wing. So this is belong to the finite element quantity, and again is a low Markov. We want to calculate the right hand side bending moment, and then it refers to 101 low Markov, and we use the global aerodynamic coordinate, and we want to take the moment about the x-axis. Okay, so that will give us the right hand side wing bending moment, and this is referred to the panelist car to list out all the panels on the wing, and this refers to a set 1 car, and those grid points are located within the wing. So this will give us the initial load. This will give us the aerodynamic loads, and the net loads will be integrated to obtain the bending moment. And this bending moment of the left hand side wing. So we put LHS, meaning the left hand side. The last one, we want to compute the stress in this C bar element with ID 110. So this is a modal. Okay, then it refers to a DMI car. The DMI car, the two DMI car. This DMI car is import the stress, the modal stress of those modes, and this refers to another DMI car, and in this DMI car, it lists out the modal stress due to the anti-symmetric modes. And in output, this trim module always output the aerodynamic stability derivatives. So the first it will output the longitudinal aerodynamic stability derivatives. If you have a full span model, it will call asymmetric aerodynamic stability derivatives. The first one is called thick-end. There's a mean flow, and this is a drag, side force coefficient, lift and rolling moment, the pitching moment, and yawing moment. And all the forces are normalized by the reference area, and the rolling moment and yawing moment are normalized by the reference area and the reference span, and the pitch moment is normalized by the reference area and the reference chord. And all the moment center is at this value. This is specified. They are specified in the Aero Z car. And so this is a thick-end. Next is alpha. Alpha, Q-ray, canal, and Trinity flap. They are all longitudinal or symmetric aerodynamic stability derivatives. So this is for example, this is dCd by d alpha in one per degree, and this is CL alpha per degree. This is CM alpha per degree. This is a pitch rate. This is a CL alpha, CLQ. This is CMQ. This is canal. This is CL delta. Delta is canal. This moment CM delta is canal. Likewise, this is for Trinity flap. Next, it will print out the lateral aerodynamic stability derivatives, and this is beta. This is roll rate. This is yaw rate. This is aileron. This is a rudder. So for example, this is CY beta. This is CL beta. This is CN beta. Okay. Okay. And after that, you will print out the trim solution. First, you will print out the trim degrees of freedom, and is because N, Y, NZ, P dot, Q dot are all the user input. Okay, it's given. Okay, so we give 4G here, and other are 0. This is for flexible. This is for rigid, and then we print out the trim variable solution. The first one, thick-end, is given, so it is 1, and the alpha is computed. So for the flexible aircraft, it's 0.75 degrees. For the rigid, it's 1.5 degrees. And the Q ray is input, and the canal is computed. So this is unknown. So the canal is for the rigid is 4.2 degrees. For the flexible is 4.7 degrees, and so on. So this is for flexible. This is for rigid. This is the unit, and then after that. The trim module will integrate all the aerodynamic forces and aerodynamic forces to get the force and moment coefficients, and it will print out for flexible, for rigid, and so the induced drag is that much, and the lift is 0.16, and so for both rigid and flexible, because we need that much lift to give us a 4.8 G pull up, and then this the pitch moment. The pitch moment is also is the same, because this requires a pitch moment, and this value is not 0, because for the trim condition we have to satisfy the 0 moment. And why it's not 0? Because this moment is about the aerodynamic moment center. It's not about CG. However, if you convert this pitch moment to the CG, you will find out that the pitch moment is exactly 0. So this solution shows that in order to achieve a rolling pull out at 4.8 G, and Q rate is that much, we need the angle attack 0.75 degrees. But in the trim flat car, the mean flow is at 1 degree. So actually the actual angle attack is that much. The delta we need 4.749 degrees, but in the trim flat car we specify the canal equals to negative 1 degree. So this is the true canal deflection angle. This is the beta. This is the roll rate, and delta for the rudder we need 1.36 degrees. And after that, you will print out the generalized coordinate solution. For symmetric modes, we have 21. For anti-symmetric modes, we have 16. So you will print out the generalized coordinates of the symmetric modes and for the anti-symmetric modes. At the end, you will print out the trim function, because we asked for, we define 4 trim function. This is the hinge moment of the right-hand side aileron, the bending moment of the right-hand side wing, the bending moment of the left-hand side wing, the stress at the C bar 110. This is the rigid value. This is the flexible values. And if you do the nonlinear flutter analysis or ejection loss analysis, because those analyses are nonlinear, and so the initial condition of the starting point must be specified. So in those two modules, you need to obtain the initial modal coordinate solution. So this output sometimes you need to cut and paste back to the ejection loss and nonlinear flutter analysis input file. The next sample case is a symmetric level fly, and you're using 2 control surfaces, because we have a canal and we have a trailing edge flap. In order to achieve a 1G level fly, NZ equals 1 and Q dot equals 0. So we have only two trim degrees of freedom and 2 trim equations. And we define 4 trim variable: alpha equals 3, canal equals 3, trailing edge flap equals 3, and thick cam equals 1. So we have 3 unknown trim variables. We only have 2 equations. So this is overdetermined trim problem. So we need to define a trim OBJ and trim constraint function. And this trim OBJ refers to a trim function car, which is a CDR, is induced drag. So we want to achieve the 1G trim condition. Meanwhile, we want to find out the optimum control surface deflection in order to have a minimum induced drag. For the constraint function, we want to define the trailing edge flap, the hinge moment of the trailing edge flap, to be less than 900 pounds. And because this hinge moment can be either positive or negative, so we have to define a trim. This 10 is a trim function which is specified before, which is the hinge moment of the trailing edge flap. And then we take the square, and so make it positive, and less than squared 900 square. So this the trim car, and then this one refer to the trim OBJ. This one refer to the trim car, and then we have a nx ny to be none. The p dot equals none, q dot equals none, and nz equals 1, because this space has a g, so it's 1g, and q dot equals 0. So we have 2 trim equations, and we have the angle attack, canal, and the trailing edge flap to be free. So we have 3 unknowns, 2 equations. Therefore, we need a trim OBJ and trim concom. Uh, so on the output, you will first print out again. You will print out the trim function. Okay. The trim function, the induced drag, function value is itself, but the objective function is because let's look at the trim objective function, because we take a square, because we want the induced drag to be a positive value. So this trim function, this the square of this value to be minimized, and then the constraint function, and this function itself, and less than this is the 900 square, and so it satisfies that. And this is for flexible. This is for rigid, and the constraint function for flexible aircraft, this is satisfied. For rigid aircraft, and this one is satisfied. And then we print out the trim degrees of freedom. NZ equals 1, Q dot equals 0. They are used input given value, and for the trim variable and alpha cannot training flap are computed. They are unknowns. So this is for flexible. This is for rigid, and then you would print out the force, aerodynamic force and moment coefficients, and this is flexible. This the rigid. Okay. So this is a alpha, canal, and trailing edge flap.